Thanks for inviting me and for the opportunity to talk to you about LOD and LOQ. So I'll start off by saying that I am not an expert on LOD, LOQ or detection methods and things like that. So I kind of ran into this project when we were working on Study 9 with Sue. So I think she's presented other parts of Study 9. And during the process, I was corralled into an office and said, you need to calculate LOD and LOQ for all these peptides. And so I kind of hobbled through what literature there was and kind of tried to figure out what methods people used. And one of the things I did want to do was to make it practical and pragmatic. So there, I'll actually give you an example during the talk, but there are several methods of calculating LOD and LOQ that can be so complicated that it really doesn't work for practical situations where you have 3 to 4 replicates and lots of peptides, and you need to calculate these on a quick turnaround basis. So you could do a research project, but you needed a method that was quick, easy, and kind of simple. It shouldn't be simplistic in the sense that it doesn't give you reasonable answers, but you wanted a simple method that would work under most circumstances. And so that was kind of my goal. And I'll just go through what kind of background research I did and what we ended up implementing, and show you a reasonable comparison, and kind of summarize at the end what went into Quazar and what you can get as of today. So first of all, just basics of what you mean by detection. So when you're running your targeted assay, you're calculating estimated concentrations for things that you have in your sample. So what are the kinds of things you would look for when you're looking at detection? So first off, when you're given an observed signal, so here signal means your actual intensity or peak area ratio or however you want to interpret it. So I'm going to kind of keep this a little bit general, so you can apply it to other things, but ultimately it was applied to targeted proteomics. So given an observed signal, you need to decide whether your analyte or your peptide of interest was actually present in the sample. So that's kind of your first job when you look at detection and limits of detection. The second thing is you have a pre-specified measurement process that you have. So you have your SOP laid out and you know exactly what you're going to do. For that process, you need to calculate the minimum level in which your peptide must be present in the sample so that you will get a signal that says your peptide was detected. In other words, if it's there in your sample, you want your system to come back and say, yes, it's there. So what is the level of the peptide in your sample so that you can always have that with very high probability. So that's the second thing you want to do. And finally, when you start analyzing real samples using the assays that you have configured using targeted proteomics, you also want to be able to measure things with precision. So you have 100 patient samples and you're measuring 30 proteins, and you want to be able to measure those proteins with very low CVs. So what levels should those peptides or proteins be in the sample so that you can measure them with very low CVs? So those are kind of the things you look at when you look at detection and measurement. So to lay these out to the limits that people usually calculate in these kind of targeted assays. I found that this paper by Lloyd Curry, so Lloyd Curry is an authority on limits of detection, and he has a very old paper written in 1968 that I think very clearly lays out the statistical principles and background on what you do when you do limits of detection and quantification. And so the next few slides are kind of basically summaries from his paper, but I found it very illuminating to kind of understand what limits of detection and quantification are all about. So when you're looking at signal measurement and limits, so first of all, I'm going to start with the caveat that whatever I'm talking about today is all about lower limits. How low can you go? There is a corresponding issue with going too high. I think Sue mentioned saturation and upper limits. So there are upper limits for systems, but I think those are a little easier to find, and also the lower limits are what people are mostly worried about, because when you're running a cancer sample, in most cases you want to be able to measure the really low intensity or low abundance peptides. And so that is, I think, a bigger problem. If you have too much of it, you can always dilute it and run it. But if you have too little, it's very hard to increase the levels to make it measurable on a mass spectrometer. So I'm going to be talking mostly about lower limits in signal measurement. So there are 3 limits people calculate usually. So the first one is what is called the critical level, or sometimes called the limit of blank, or LOB. And this kind of corresponds to the first thing that I mentioned here. So when you have a signal, when do you say that you have detected the analyte? So that corresponds to the critical level. So here you're deciding whether you have detected something, essentially using statistical hypothesis testing after you have made the measurements. So you make all your measurements, and then you decide, you figure out this critical value. And if your signal is beyond the critical value, then you say, yeah, I saw it. So here there is no process. It's like a ad hoc thing for the specific thing you're measuring. But when you start having a process, you not only calculate the critical level, but you also calculate this thing called the detection limit, where you can a priori say that if the analyte is present at this level in my sample, I am going to detect it. So that's called the limit of detection, or the lower limit of detection. So it's usually, the paper, Curry's paper uses LD, but LOD is like the common representation that people use. And LOD is used for qualitative analysis. So you can't use it for doing fold changes between cancers and controls or something like that. So you use it to mostly say whether things were there or not, and kind of get approximate qualitative assessments. So when you want to go and do quantitative analysis and actually believe the measurement you made, you look at this other limit called the limit of quantification, or determination limit, as Curry calls it, where you can not only detect your analyte, but you are also sure that you are measuring it with reasonable precision. So you have sufficient, so what is sufficient depends on what you're doing, but usually 15 to 20% CV is considered a good measurement. If you have better, it's even it's fine. But so you are measuring something at sufficient precision, so you can use it for quantitative analysis. So that is the limit of quantification. Is there a question?
I have a question.
Yeah.
LOB is the limit of blank.
Yeah.
What's the difference between LOB and just noise?
I'll get to that.
Okay.
So you use the noise to determine LOB, basically. Yeah.
Okay.
So actually, it's here. So if you assume that you're measuring the blank, let's say, so you know there is no analyte for sure, and you're trying to measure your analyte, you are going to get some signal, which is usually noise. So you make repeated noise measurements, and you assume that your noise is kind of distributed normally with mean 0, because this is the blank. Your actual measurement is 0. So you do that, and you also have a standard deviation for the distribution of your noise. And so the limit of blank is usually defined as some percentile of the standard deviation that you have measured for the blank sample. So here we are making the kind of ideal assumption that when you measure something, it's centered at 0 and distributed around 0, which is not quite true, because you don't have negative measurements in mass spectrometry. We'll get to that part later, but assume there were. So you had a perfect measurement system. So then you just inject your blank multiple times. You measure the standard deviation of the blank, and let's say if you want a 95% confidence that you will not make a false call. So in other words, the false positive rate is 5%, or your p-value is 0.05, which is the alpha that is mentioned here. Then this k alpha is basically the critical value. It's called the normal distribution critical value for the 95th percentile. And usually for a one-sided distribution that comes to 1.65645, I think. So you measure the standard deviation of the blank, and 1.6 times standard deviation of the blank is your limit of blank. So your critical value is now essentially characterizing how widely is your noise distribution, how wide is your noise distribution. And so that gives you your critical value. So now if you make a measurement and your measurement was 5 times the standard deviation of the blank, then there is a very small probability that it is actually blank. So there is a very high probability that you are actually measuring something in your sample. And so you say your analyte was detected in your sample. So this is like after doing all your measurements. Does that answer? Yeah.
So is this at specifically the retention time of your analyte, or is it across the entire?
No, this is for a specific analyte. So a specific peptide or even like a specific transition. So that is at a specific retention time. And you would do this, so if you are measuring 10 peptides and 3 transitions for each peptide, you would have 30 measurements overall, and you would do this calculation for each one of the 30. So that's what Quazar does actually. So for every transition, it goes and does all these calculations. So now the limit of detection is saying, okay, so now if something is above the critical limit, then there is some small probability that it is a false positive. So let's say there is basically we're close to 0 probability that it's a false positive. But when you actually have a sample at a specific level, so that is the lower distribution here, it's possible that these two distributions could overlap depending on how far apart these the means of the distributions are. And so it's possible that when there is something, you could think it's a blank. So it's the probability of a false negative. And so you want that also to be small. So in other words, you want to shift the lower distribution as far away as possible so that there is minimal overlap. And how far do you shift is what determines your LOD, or limit of detection. So usually the beta here is the false negative probability, and generally you set that also to 5%. So when your alpha and beta are both set to 5%, then you get your limit of detection. So this formula is basically saying you take your critical limit, which is this line, and then you add the number of standard deviations you need to go in order to get to this mean. And so when you get there, that's your limit of detection. And if you assume that the blank and when you have sample in your measurement, the standard deviation that you get is approximately the same. In other words, the standard deviation of the top distribution and the bottom distribution are approximately the same. You're assuming that your sigma naught, or the standard deviation of the blank, is approximately the same as the standard deviation when you have an analyte in your sample, and your false positive and false negative rates are 0.05, then you can see that the limit of detection is approximately 3 times the standard deviation of the blank. So that's the formula most people kind of use. So it's actually 3.29, but people just approximate it to 3. And generally 3 times the limit of detection is taken as the limit of quantification, where you are high enough that you can quantify with reasonable precision. And so when you multiply 3.3 by 3, you get approximately 10. So the things shown in blue are the usual kind of accepted definitions that people use for LOD and LOQ. So you measure your standard deviation of the blank, 3 times the standard deviation of the blank is your LOD, and 10 times the standard deviation of a blank is your LOQ.
Usually mean sigma is the OB is the LOB, and also 10 times the sigma is the LOQ is the same one, right?
Yeah, it's kind of based on the same principle, but in many instruments, it's not clear what the signal to noise is. So signal to noise is kind of supposed to represent the standard deviation of the blank. like I was saying, depending on the software you use and the instrument you use, what signal to noise represents is a little unclear. And so it would be best if you used a real blank sample and then did your measurements. So now, up to now, we were kind of in the idealized world of normal distributions with zero mean, which is not really the case. So when you actually do a measurement, the mean, the blank is not going to have a zero mean. It is going to have some positive mean. And so then what you do is you kind of subtract the mean of the blank, and then you define that as your net signal, and then you use that in your calculations. In other words, when you calculate the LOD using this formula, you add the mean of the blank back in, because your LOD is that much higher, because when you just have the blank sample, you have some mean value in it already. So this is kind of like a practical thing that happens because you can't measure negative numbers. The other thing that complicates things is when you have an endogenous level. Then I think Sue mentioned it earlier, and I'll briefly spend a slide later on. When you have an endogenous level and you're increasing your light spike or decreasing your light spike, at some point your spike is going to be comparable to the endogenous level, and so you won't have a straight line curve anymore, and then it becomes difficult to say how you are going to measure LOD or LOQ. We'll address that briefly later. Any questions up to now? Okay. So in order to deal with the fact that when you make actual measurements, you have you're not really in the realm of the idealized normal distribution with zero mean. There was this paper by Christian Linnet where they used an empirical approach to kind of deal with that part. So here you see two curves here. So one is labeled blank. The problem is that the part below zero is not observable because you make measurements that are positive. Whereas for a sample, you most probably see the normal distribution. So what they did was, in order to kind of deal with the non-negative issue for the blank, they use an empirical calculation for the 95% confidence interval. So instead of using the normal distribution and the normal distribution critical value to estimate the multiplying factor for your LOD, what they do is they run the sample multiple times with just the blank, and then calculate a 95% confidence interval and then use that. And then for the actual sample where you have the analyte spiked in, you can just estimate the standard deviation directly. So the problem with that is, in order to estimate a 95% confidence interval, you usually need approximately 20 replicates, because the resolution of 20 gives you steps of 0.5 increments, because 1/20th is 0.05. So you get 5% increments, and so to get 95% confidence interval, you usually need about 20 replicates. And that's a lot of replicates, and in mass spectrometry, most people don't run that many replicates. Actually, for study 9, we had 3 or 4 replicates, and even that people were saying, do we need that many? So that's generally the approach. So this may not completely work. So what we did for the CPTAC study 9 was basically to say, we'll just use a t distribution to approximate for the finite number of samples that we use. So instead of the normal distribution number of 1.645, we just use the t distribution. The number of replicates kind of gives you the degrees of freedom, and so the fewer replicates you have, the larger your multiplying factor is going to be. And so what we have here is, this is the mean of the blank, which I said you need to kind of account for. The first term is the standard deviation of the blank. The second term is the standard deviation of the actual signal. So the other thing that we assumed when we did the Curry method was that the standard deviation of the blank and the standard deviation with the analyte in the sample are the same. That may not be the same. And so in order to account for that, we actually use what is called a low-level sample. So you take your calibration curve or your sample spike-ins, pick the sample with the lowest spike-in level that you had, and then use that to determine the standard deviation with the for the sample with the analyte, that is sigma d, and then you use your sigma naught, which is the standard deviation with blanks. And so this formula was kind of what was used to calculate LODs for the CPTAC study 9 that Sue mentioned. So I'll go through a couple of other methods that we explored during the process of coming up with this, and then kind of show you how those compare with the method that we finally used. So this method uses the entire calibration curve in order to find the LOD. So essentially what this does is you fit the regression line using all the concentration points in your calibration curve. And then you calculate the standard error. So, and then once you have your regression line, you have your what they call the y hat, or your predicted values for the actual values that you have observed. And so you can calculate the error of the regression to the actual observations. And so you calculate the standard error for your regression line. And then you use that instead of the standard deviation of the blank or the standard deviation with the analyte in it. So essentially you're still using the same formula of 3 times the standard deviation as LOD and 3 times the LOD as the limit of quantitation. But instead of the standard deviation derived from either the blank or the sample with signal, you use your regression line to derive the standard error, and then you use that. And the other thing here is you divide by the slope. So usually you assume that the slope is 1, and so in these examples where we use just the blank or the blank plus the low concentration sample, we assume that the response is linear and the slope of the regression line is 1. So we don't divide by the slope. But that may not always be the case. Like the examples that Sue showed, some of them had a slope of like 1.01, others may have a slope of 0.97. So the slope may be slightly different from 1. And in order to account for that, you kind of divide by the slope. So this you can apply in general, irrespective of which method you use, but in this method it's explicitly taken care of. The other method that we looked at was kind of looking at things in a reverse way in some design. So in most of the others, we have calculated the limit of detection, and then 3 times the limit of detection is taken as the limit of quantification. In this method, which we call the RSD, or the relative standard deviation method, you calculate the limit of quantification. So you calculate LOQ, and then you calculate your LOD as 1/3 of that. The reasoning is that when you want to be precise, when you want to worry about precision of quantification, why don't you just look at the precision, model the precision along the calibration curve, and find a point where the precision is like at the limit that you want it to be. So that's kind of the philosophy behind this. So for people who are not familiar, RSD is same as what is called relative standard deviation is same as CV, which is coefficient of variation, and is calculated as the ratio of standard deviation to the mean. So it's kind of the standard deviation based on where the mean is located. So you first select a target value for CV or RSD. You say 20% is the minimum precision that I want. So anything below 20%, I'm fine. Then what you do is you run your standard curve with multiple concentrations. The paper, which is referenced here, recommends at least 6. So if you have around 5 or so, it's okay. If you have just 2, I think this method is not going to work. But if you have more than 6, it's fine. Then you calculate the RSD at each concentration, and you use this second equation here to model the RSD as a function of concentration. And this equation, when you take the logarithm, actually becomes a linear equation in the log values. So it's relatively easy to calculate the constants and get the equation. So once you do that, you kind of ask, at what concentration point do I hit 20% RSD? And that is your LOQ. And your LOD is 1/3 of that. So that's how you do with this method. So any questions so far? Okay. So the last method I'm going to show is what is called a variance-based model for determining LOD and LOQ. So this is what the statisticians were actually doing in the beginning of the project, and it was getting so complex and answers were kind of difficult to consistently get, and the model was so complicated that the data we had was not enough to actually get a reasonable model. But I'll quickly go through what happens here. So here you calculate your peak area ratios, that is your analyte divided by standard, that's light over heavy. And then, like I mentioned earlier, this assumes that each sample, so here sample means a specific concentration. And each concentration you have a different variance, which is true, because as your concentration increases, your actual standard deviation value increases. That's one of the problems with fitting the regression line for these kind of experiments. You have to account for the fact that the standard deviation increases as your concentration increases. So this one explicitly assumes that at each concentration value, there is a specific value of variance. And that variance or standard deviation is a function of concentration. And they kind of come up with a variance model, almost like a regression model for the variance, and then estimate the variance for each concentration point. And based on this variance, they use what is called weighted linear regression. So this matrix is basically based on the variance at each sample point, sample concentration. And based on that, they calculate the regression line. So once the regression line has been calculated, they calculate the mean square error, or essentially the standard error for the regression, and then use that basically in almost the same way, where you have 3 times the error gives you your LOD, and 10 times the error gives your LOQ. But the key is that the error is now based on the entire concentration, the calibration curve, taking into account the fact that the variance changes at each of the concentration points, and also taking into account that there is an overall variance that is not accounted for by concentration. So it has a very complex variance model, but because of the complexity of the variance model, you need a lot more data than like 3 replicates per point in order to fit this properly. So there were issues in fitting this model, and this model was I think Cliff Spiegelman at Texas A&M, his group came up with the model for the data. So here are some comparisons. So we ran all the 5 methods. So I have in black when I say calibration, it's the method based on the entire calibration curve. The red is what I say Linnet is the final method that we used, which was based on the t distribution. RSD is the one based on RSD or CV. What I call statistical is here is the Curry method, which was based just on the blank, and the variance modeling method is what is called TAMU here, because it was from Texas A&M. And for the panel here shows each row of 3 is one peptide. So 169 is the number given to a specific peptide, and you have transition 1, transition 2, transition 3. So similarly so we have 4 peptides here, and we are looking at 3 transitions per peptide. And so if you take 161 transition 1 and look at the red lines, the lower line is the limit of detection, and the upper line is the limit of quantification. So the LOD and LOQ are marked as bars for each of the methods. So straight off you can see that the what I call the Linnet method and the statistical method are almost always the same. They're approximately the same. In some cases, I think the Linnet method gives slightly higher values because the variance of the measurement when there is an analyte is actually slightly higher than the variance of the blank, and so that is taken care of by the Linnet method. The other thing you notice is that the RSD method, the green one, for this peptide it's like way high. So the fit was not very good. In some cases actually I think it can be really low. So the RSD method is not very robust and could result in wild changes in some situations. So I think it depends on the behavior of the peptides. If the standard deviation is actually very well behaved and increases properly, then it works reasonably. Otherwise, it doesn't. And finally, the Texas A&M method actually in some cases results in very high values. So here, for example, in 166, it's quite high, and there are similar examples here. So you can see here it's quite high. For badly behaved peptides like this, there's not much you can do anyway. So I think the point here is to show that the Linnet method is reasonably robust, works for most cases, and gives answers that are practical. And I mean, when we did these, there were mass spectrometrists who were sitting at it and looking at the actual the curves and the LOD values and checking if they would agree with that in a reasonable way. That method kind of was the most robust that we found, and that was what we ended up using for the study. So a quick comparison, I think you can, I don't want to go through this line by line. I think I have pointed out most of the advantages here. So practical considerations, which method would you use when? So again, it all depends on the kind of experiment. Many times people come and say, well, I ran my experiment, there's no blank, can you calculate an LOD? And obviously you can't use the Curry method or the Linnet method. So you could use the RST method if they had multiple points. So it all depends on the experimental design. If you have control from the beginning, that's perfect. You can get the right number of points in the right concentration ranges and do it. But otherwise, it's going to be, it depends on what the experimental design was. So quickly, I think Sue showed most of the Quazar functionality, so I won't go into that. This is to kind of say, I think Quazar grew out of the LOD work that we did, and we added on other things that is now available as this package in Skyline. And also separately, if you don't want to use Skyline, you can also use it at GenePattern.Broad Institute. It's a standalone thing. And salient features I won't go into, Sue already showed it. I'll spend 2 minutes on endogenous detection and then I'm done. So if there is an endogenous level present in your sample and your range, that the concentration range you're looking at is reasonably linear, then you expect your calibration curve to just shift up. And so the idea is, if you can find the y-intercept and you can statistically say that the y-intercept is not 0, then whatever the y-intercept is, that is your endogenous level. So that's kind of the simplistic assumption that it makes. I mean, it works when all the assumptions are satisfied, but in many cases it may not work. So this is like a kind of a back of the envelope calculation for doing endogenous levels. So we fit the regression curve, the regression line, and statistically determine whether the intercept is 0 or not using a bootstrap sample estimation. And then if we can say that the intercept is non-zero, then there is an endogenous level, and the actual value of the intercept gives you the level. And the principle is kind of illustrated here with simulated data. So the red line is the ideal line. And if there was an endogenous level of 2.0, I just randomly generated some data, and this is the line you would get. And here you can see that this says the endogenous level is 1.82, which is reasonably close to 2. And that's pretty much it. So if there are any quick questions, I can take it. Otherwise, there is a list of references. I can make these slides available. And any questions?
Great.
Okay.